Okay, you saw the thumbnail. We're gonna compute this particular limit. The interior of sine goes to infinity, and one might think that because of the oscillations that will always exist for sine, this may not have a limit. But the truth is that the expression inside sine will increasingly be very close to multiples of 2 pi, to integer multiples of 2 pi. And that's why the sign of those expressions will be very well estimated by sine of integer multiples of 2 pi, which have 0 sign. And therefore we expect a limit of 0 for this. But let's get down to the rigorous solution. So because I don't want to deal with large quantities and it's difficult to come up with estimates about them, I want to rewrite my 2 pi n squared plus 1 as my 2 pi n root 1 plus 1 over n squared. So of course I didn't change anything, simply pulled out 1n from that root and of course divided to pay for it. Now this quantity here is something that I wish to deal with because it's very close to 1 obviously, but I want to get some clear estimate on how different this quantity is from actually 1. And to deal with that, if I write it as this expression, then this is exactly equal to f of 1 over n squared minus f of 0 divided by 1 over n squared, where f of x is given by root 1 plus x. So please check that if you plug in 1 over n squared and 0, you recover the quotient on the left-hand side. So by mean value theorem, we know then that this quotient, so 1 plus 1 over n squared minus 1 divided by 1 over n squared equals f prime of c for some c between 0 and 1 over n squared. And as a result, 1 plus 1 over n squared root, which is something bigger than 1, and therefore this quotient is positive, is equal to, well, derivative of f is quite easy to compute, 1 plus x, and we computed at c, so this is that. But how big can this be? This will be never bigger than 1/2 because c can be 0 but not less. And if I multiply by 1 over n squared on both sides, I get that 1 plus 1 over n squared minus 1 is less than 1 over 2n squared and positive. So where am I getting from here? The answer is that now I multiply by 2 pi, so I get that 2 pi n, I multiply by 2 pi n of 1 plus 1 over n squared minus 2 pi n is less than or equal to pi over n. And notice that this quantity is just the original quantity inside sine. So 2 pi n is less than pi over n and bigger than 0. Now, notice that sine of 2 pi root n squared plus 1 is equal to sine of 2 pi root n squared plus 1. Same thing, minus 2 pi n, because if I add or subtract any integer multiple of 2 pi to the angle, the sign does not change. And therefore, this quantity that I wanted equals this quantity, and but we exactly have some upper bound and lower bound for this. So we see that the difference here is some angle between 0 and 2 pi. So this will be no bigger than sine of pi over n. And so far we haven't fixed any n, or n doesn't have to be large. So for every n in natural numbers, we have this estimate on the sequence. So if n goes to infinity, the right hand side goes to infinity, and that is absolute value, then sine of 2 pi root n squared plus 1 also goes to 0, the end of the story. So that's it. A beautiful application of mean value theorem, and also a warning that simply because the inside of sine goes to infinity does not mean the limit does not exist, because there may be pattern to how they actually converge to infinity. And last but not least, keep this trick in mind that you can always subtract or add multiples, integer multiples of 2 pi to any expression inside a sine. And that was the key here, because we had something that was going to infinity, and to offset that, we subtracted an integer multiple of n, and all of a sudden after the subtraction, the angle was actually something very tiny. So we crushed an infinite angle into a tiny angle. I hope you enjoyed this video, and hope to see you soon in some other videos. Please subscribe if you haven't yet.